So let's go ahead and talk about the activity. And like I said, we're going to go through this kind of a piece at a time. The two pieces that I want to cover today are the things that we did at stations 2 and stations 3, okay? So go ahead and go to the one that says relationship 2. That's the one we're going to cover first. You may have already answered all these questions. That's okay, especially if you answered them right, then that's good. Now, if you weren't sure how to answer some of these, I'm going to help you out with it, okay? And if your answers are wrong, then I would recommend changing them as we go over it, okay? So examine the setup, make notes on your observations. Just as a reminder, this was the setup for Station 2. It was the 2-liter bottle with the inverted test tube in it, okay? Now basically what's happening here, and you guys all saw this, right? This was the easiest one to do because all you had to do is squeeze the bottle, and the test tube falls, right? Anybody have a good idea of why exactly that might be happening?
When you squeeze the bottle, more water enters the test tube and compresses the air to the top, which makes it less buoyant, so it floats down to the bottom, and when you release it, it expands here.
Okay. I need that on here because that's about as good as I could have done it, I think. And I'm not sure that all of you heard that, okay? So can you say it again a little bit louder?
Yeah. When you squeeze the bottle, more water enters the test tube, which compresses the air to the top of the test tube and makes the beaker less buoyant, so it falls to the bottom. And when you release it, the air expands again and it rises to the top.
Okay. So basically what we're doing here is we are changing the density of the test tube by forcing more water into it or out of it, right? Okay? Now, the most important thing he said there was that when we squeeze the bottle, it compresses the air. Everybody hear that? Okay? That's the important thing here as far as this relationship. That's why we did this activity, is to show you the relationship between pressure and volume. Okay? So observe what happens to the test tube. You probably got that. It sinks when you squeeze it. It floats back up to the top when you release. So here's the actual questions I want to talk about. Why this is happening to the test tube. So you probably want to write something along the lines, and I'm not going to write it out exactly for you because this is a video and that would be too easy if you just had the answer sitting right there on a video. But basically, lost my train of thought because I was thinking I guess it's pretty easy anyway if I'm talking with you about the answers, but oh well. So the reason this is happening, again, is because we're forcing water into the test tube, okay? As we squeeze the bottle and force water into the test tube, it causes the test tube to sink because now the test tube is denser than it was before. Okay, something along those lines. Does everyone understand how we're increasing the density of the test tube? How is forcing more water into the test tube increasing its density?
Water.
Well, what's more dense, water or air?
Air. Water.
Yeah, water is quite a bit more dense than air, right? Okay? Given the same amount of volume, 100 milliliters of air weighs hardly anything at all. 100 milliliters of water has some actual weight to it, okay? So, and weight and density are not exactly related, but, if you're talking about a volume, then they are. Point is, if we force more of the water into the test tube, the water's more dense, so that makes the test tube more dense, so then the test tube is going to sink in the water, okay? That's the idea there on number 1. So something along those lines. Now, this is the important part. Based on this Minilab, what do you think is the relationship between gas pressure and gas volume? Okay, now when we do these relationships, have you guys talked about direct and indirect relationships in your math classes? Or maybe direct and inverse relationships? No? Have we talked, and we haven't talked about that in here, have we? Okay. All right, so a direct relationship basically means that if one thing goes up, something else that's related to it also goes up, okay? So in a direct relationship, if we increase the pressure, then that would mean that the volume also increases. Is this a direct relationship here that we're talking about? Okay, so let's think about it. So I'm increasing the pressure on this gas by squeezing the tube, right? Okay. And you can actually see this. Did you guys notice this yesterday, that you can watch the air level changing when you squeeze it? Okay. So I am increasing the pressure on the gas. What happens to the volume when I increase the pressure on the gas? What happens to the volume of the gas? So remember, volume is the amount of space it takes up, right? Thank you. So does the gas take up more or less space when I squeeze it? The gas takes up less space, so the volume decreases, right? Okay? So as I increase the pressure on the gas, the volume of the gas decreases, gets smaller. Okay? That's what we call an inverse relationship. Whoops. Where'd you go? All right, so as we increase the pressure, the volume decreases, okay? And that's the actual relationship that's happening here. Now, if you want to write that in words, which, oh, come on. It might be better to write that in words. But something like, as the pressure on a gas increases, its volume decreases, okay? One goes up, the other goes down. As the pressure on a gas increases, its volume will decrease. And that is called an indirect, you don't necessarily have to write this here, but that's called an indirect or an inverse relationship. Okay? All right, everybody okay with this is called the Cartesian diver. The reason for that is because this is the way that scuba gear works, okay? Or the way a submarine works, for that matter, right? The submarine takes in extra water in order to be able to sink, right? Kind of like this test tube is taking on water in order to be able to sink, okay? All right. Station 3, that's the one with the hot and cold balloon, okay? So you had the balloon that you put in the freezer, measured the circumference. You measured the circumference at room temperature, and then you measured the circumference at, well, when it was in the hot water bath, okay, or directly above the hot water bath. So this one, I had a couple of groups that were getting weird data on this one. Don't change your data, okay? It's fine. You're not going to get counted off if your data is weird. But what you should have seen happening here is that at room temperature, well, let me say this. Temperature of the gas when, the circumference of the gas in the balloon, once you put it in the freezer, it should have gone down, okay? So I think one group yesterday had like 21 centimeters for the diameter at room temperature, something like that. Is that right? What do you guys have? Because I was talking to you guys about it. Do you remember? For the room temperature. 22 centimeters. And then in the freezer it was 21, okay. So it went down a little bit, okay. Not a huge amount. If we had had dry ice, then you probably would have seen it more drastically, because dry ice is colder. But it did go down a little bit, okay. So from 22 centimeters to 21 centimeters. Then, when you put it in the hot water bath, you should have seen your circumference go up. And actually, I feel like, maybe it's just my imagination, but I feel like when I set those on the hot water baths, I could see the balloon getting bigger, right? Did you guys feel like you could see that when you were watching it? Some of you yes, some of you no, okay. Again, I knew what I was looking for, so maybe I was just, my mind was playing tricks with me or whatever. But what did you guys get for your hot water? Okay, so it about went up a centimeter in either direction, depending on whether it was in the cold water or the freezer or the hot water. Okay, so you should have seen it go down a little bit, the circumference go down a little bit when you put it in the freezer, and then you should have seen the circumference of the balloon go up a little bit when you put it in the hot water bath. Okay, and again, you don't have to change your data now if it doesn't match with that, but you just need to be aware that's what should have happened. Okay. Based on this Minilab, what do you think is the relationship between gas temperature and gas volume? Okay? So gas temperature and gas volume, I don't know. My smartboard's weird. So if we increase the temperature, what would I say about the volume of the balloon? Yeah, it should increase, right? So increase the temperature, increase the volume. That's a direct relationship, okay? Does that make sense? You decrease the temperature of the balloon, you're going to decrease the size of the volume of the balloon, okay? You might kind of know this one just from experience. Has anyone ever taken a birthday party balloon outside after a birthday party on a really cold day? And it's like, oh, what happened to my balloon? Because it starts to deflate, you know? And then you get it back in the warm room temperature air, and all of a sudden it's fine again, okay? It's the same idea. A gas will shrink or contract as you cool it down, and it expands as you heat it up, okay? Can you guys think of any other examples of a time when that happens? Okay, tires is a perfect example, right? Your tire might look a little bit flat in cold air, cold weather. Once you drive on them for a while, that air starts to heat up because of the friction of the tire on the road. And then you might get somewhere, and now your tire doesn't look flat anymore because you've heated up the air that's inside the tire, okay? So, perfect example. All right. Does that make sense to everybody? Okay. So those are the two, those are the two relationships I wanted to talk about right now. That's as far as we're going to get on the lab for today. So just hold on to that. We'll keep talking about it, and then we're going to do some notes on the two laws that relate pressure and volume and temperature.